Okay, welcome back. So in this one, we're going to check the application areas for quantum computing. We're going to basically understand them from a problem-related point of view rather than focusing on the complexity as we did before. It's a classification that you know by now, but I think it's interesting to have it in mind in order to understand how the next videos are going to explain the different challenges. So it's really close to what we discussed in the previous video, but this one is probably simpler or more oriented towards an understanding of the final application or the business application. We have the problems that we can efficiently address today. So that's something that is not going to be relevant for us because let's face it, if we have a solution that is already mature, is less expensive, is readily available, that's probably something where we are not going to use a quantum computer. And then we have problems that we can't adequately address today. Out of those, many will still not be viable for a quantum computer, so those are also out of the question. But we will find some areas in which this is going to become interesting, and actually, not everything. Oh, nice. I was trying to change the color. Um, no. Not everything within that group is properly identified. We may find that even problems that were not identified start to become interesting as we progress with this technology, because we may be able to find that some things that we start to be able to solve with quantum computers can actually be reused or can actually unlock additional applications. So that's going to be one of the areas for interest. We have to identify which problems fall within this area, and of course, we have to keep in mind that not maybe everything needs to be addressed only with a quantum computer. In many cases, we will look, as you know, for hybrid approaches, variational approaches, processes that can be decomposed in quantum and classical subprocesses. So we will use that in order to understand how we can solve for different problems. And then we have largely three main application areas. Not everything falls within these three buckets. There are other options in order to classify the problems, but basically we're going to be looking at optimization. So that's very related to the subject on practices with elevated quantum computing, because everything that you will see in that subject is related to this type of application. So basically knapsack problems, traveling salesman, spanning trees. So everything that has a huge solution space in terms of potential combinations on how to solve a specific problem. And then you have an objective function, constraints, global minima in order to look for the optimal solutions, or maybe you have local minima and so on. So those type of problems where you have many different solutions and you have to optimize for the correct configuration in order to find that optimal solution, that's going to fall within optimization. And that's something that has applications across all industries, I would say. Then we have machine learning. So this one is where we will have the competition with classical machine learning, artificial intelligence in things like anomaly detection, segmentation, pattern recognition, forecasting, and so on. Um, Depending on how you implement this, machine learning can actually be understood as an optimization problem. So don't consider this classification as something that is set in stone or anything like that, because, for example, machine learning, if it's solved with a variational quantum algorithm, that variational quantum algorithm in the end is solving an optimization problem. How do I adjust the variables of my variational algorithm? How do I optimize that configuration in order to reproduce a specific behavior for a machine learning application? So it's an optimization problem in the end. So this segmentation is not always that clean. And you also have machine learning approaches that don't need an optimization, a pure optimization approach. And then we have simulation. By simulation, normally I'm going to refer to natural simulations. So quantum chemistry, material science, physics. I'm not going to refer to, for example, to market simulation and other type of simulations that maybe fall within machine learning or other areas. And again, this line is can be understood as blurry threshold, because, for example, when you are trying to use a variational quantum eigensolver to solve um, a simulation problem to simulate a molecule, then you find yourself in a case that it's a machine learning algorithm that it has to be optimized but has applications in simulation. So don't consider this as a structured or final classification because there are boundaries that are a bit blurry, and there are also some applications that are not even in any of these three. Like for example, when we consider source algorithm, in which group does it fall? Well, actually, none of the three. So, depending on the classification that you look at or the source that you review, you may find, for example, that they also have mathematical challenges group or something like that, and they try to put short in that group, which is fine. So, try to basically have this as a way to communicate how the technology can help, but don't consider it a formal structure set in stone or anything like that. But it's useful in order to understand how to classify the different problems at the potential value, because within each one of these groups you will find a limited set of algorithms, of quantum algorithms that could be used, and that's going to help you understand, based on the potential of those underlying quantum algorithms and the type of problems or business applications that fall within each one of these groups, you will be able to analyze studies or to come up with estimates in order to understand how each one of these application areas can have an interesting potential for the future. This estimate from Boston Consulting Group is going to group applications in these same categories. They also include the cryptography potential, but this one, I don't think it refers to Shor solely. I think it refers to also quantum communications and everything, so we can leave this one aside for now. But basically, within simulation, which is the area that is expected at this point, and this changes each one of the years, but it's expected to be one of the most promising areas for advantage. You may find applications in pharma, drug discovery, computational field dynamics, solar conversion. I don't like to put Morgan simulation here, but okay. So that's the overall potential, and you can see that is the higher of the four. Then you have optimization. So optimization is challenging. Optimization and machine learning are both challenging because depending on when you look at these type of applications, you will find that it's considered to be one of the most promising application area for quantum computing, and then the next year is not considered as promising because some paper comes out and say that the advantage in some specific algorithm has been overstated, or maybe the approaches in classical computing evolve. So these two actually trade from time to time in terms of which one of the two is more promising, sorry. But in optimization, you're going to find cases across all industries: portfolio optimization, risk management, network optimization, route optimization. Some of these, as you can imagine, are applicable to several industries. And then in machine learning, which is also something that is applicable to many different cases, AI algorithms for audio-visual, like video analytics, audio analytics. Um, I don't see anything related to natural language here, but that's also something interesting. Anti-money laundering and fraud detection, search optimization, and so on. So this is commonly the classification that most sources are going to use, and it's the same classification that we're going to rely on throughout this session. There are many interesting materials. If you want to have like an overall understanding of which areas are more promising, there are many interesting materials from BCG, from McKinsey. We're going to review some of those. So it helps you in understanding if you want to look at in which area you can specialize yourself, for example. This type of analysis is going to help you in understanding which type of industry and application area could be an interesting case for you to continue developing your knowledge. So yeah, having said that, I think that's everything for now. So thank you so much for watching.